Okay, we have this problem here. We want to know how many ways can 3 light switches be on or off. The assumption here is that the light switches are all side by side. So we have switch 1, switch 2, switch 3. And we want to count how many ways each of those switches can be on or off. Since nothing in the problem says, hey, it has to, if one's on, the other can't be off, then we're safe in assuming that each of these light switches, what it does is independent of the light switches after them. So in other words, we have 3 decisions to make. For each switch, do we want it to be on or off? So there's 2 choices for the first, 2 choices for the second, 2 choices for the third, giving us a total of 8 outcomes. Those outcomes could be anywhere from all 3 being on to all 3 being off. We could list these out to save a little bit of space. Let's say we want to use the number 1 to represent the switch is on and the number 0 to indicate the switch is off. Then we could list out the possibilities. We could have on, off, on, off, 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 on, off, on, or off. Alright, so using 1s and 0s, so I don't have to write the words on and off every time. You can see that there are 8 total possibilities. So now we ask the question, what about 4 light switches? What if we do it for 4 switches? Well, again, the assumption is the 4 switches are side by side. So each switch again has 2 choices, either on or off. They're independent of each other, so we can use the fundamental counting principle. We're now going to take this idea of light switches and modify it. So we add a new question here. How many ways can 3 switches be on or off if no 2 adjacent, meaning switches that are next to each other, can both be on? Well, now with this new restriction, which I'm going to give a label here and call it restriction star. Now with this new restriction, the choices or the outcomes are no longer independent. Depending on what you pick for the first, it's going to affect how many choices you have for the second. If the first light switch is on, then the second would have to be off. You'd only have 1 choice. But if the first switch is off, then the second could be on or off. You have 2 choices. And so the only way to do that we have at our disposal is to use a decision tree. So we want to make a decision tree, and so we start with our first decision. We can be either on or we can be off. Now that takes care of 1 light switch. Then, if the first light switch is on, the second one has to be off. But if the first light switch is off, the second one could be on or off. And so we can see for 2 light switches we would have 3 outcomes. And then if the second light switch is off, then the third one could be either on or off. If the second light switch is on, the third one has only 1 choice, it must be off. And finally, if the second light switch is off, the third one could be either on or off. You see we have a total of 5 possibilities now. Only 5 possibilities. Now we can take this problem and say, well, what about the 4 light switch situation? Well, we could start all over and draw a brand new tree diagram. Or we could just take a tree diagram that we already have for 3 light switches where we have the 5 total outcomes. On, off, on, off, off, on, off, on, off, and we can just extend it one more row for light switch number 4. If the 3rd light switch is on, then light switch number 4 must be off, giving us only one possibility there. If the 3rd light switch is on, then we have 2 choices, on or off. You may want to take a moment and see if you can fill out the rest of this diagram before continuing. Now, if the 3rd switch was off, again we have 2 choices, on or off. But if the 3rd switch is on, as it is in this example here, then it must be off. And again, if it's already off, then we have 2 choices, on or off. So you can see here that we have now a total of 8 outcomes. Now this is just the last, I've just circled the last outcome, but to read the 8 outcomes you would start on, off, on, off, on, off, off, on, off, off. There's the first 3, and then you can go on and read the other 5. So I would like to summarize these results, and then I'll give you your extra credit question. Now with the restriction star for 3 switches, we discovered that there were 5 total outcomes instead of the 8 that we got without any restrictions. And for 4 switches, we found out that there were 8 outcomes without any restrictions. So with no restrictions, we discovered that for 3 switches, there were a total of 8 outcomes, and for 4 switches, there were a total of 16 outcomes. Okay, so here's your extra credit problem. You have 2 parts to it, A and B. First, for light switches with no restrictions, and B with the restriction we've been talking about. No true adjacent can both be on. For each of these, I'd like you to complete parts 1, 2, and 3. How many ways could 5 switches are there for 5 switches? First with no restrictions, and then with this restriction, no 2 adjacent can both be on. The same for 6. Once you've done that, you'll have now the results really for, you can figure them out for 1 and 2. And so you'll have the results for 1, 2, 3, 4, 5, and 6 switches. Look at those and see if you can kind of see a pattern. And then do your best in your own words to explain what the pattern is. And in part 3, once you figured out the pattern, use that pattern to go through and figure out the number of outcomes for 11 light switches. Now, as you're doing this, for part A with no restrictions, just follow what we did for 3 and 4. Okay, follow that same kind of idea for 3 and 4 light switches. For the restriction star, my advice would be to take the table, or take the diagram that we've already started making for 3 and 4 light switches, for 4 light switches, and just start on each. So just add another row of decisions. So your first light switch would be off, so that could be on or off, and branch out from there. Next one could be on, so the next one could only be off. And use that to extend this process. Now for part B, right here, I am adding one other requirement here for part B. And that is, you must have a tree diagram for part B. Okay. Doesn't count unless you have the tree diagram for part B. So for part A, you don't need to use a tree diagram. Okay. Good luck. Hopefully you have a little bit of fun doing this problem.